Aim high, dream big, and work hard. But don't forget to believe in yourself. Hello, my shimmering stars. I, Shaurya, is going to start one short video lecture on chapter Thermodynamics. Students, in our victory batch, we have already covered some chapters of physical chemistry. Today, we are going to do this one short lecture. Now, first of all, the question arises in our mind is, what do you mean by thermodynamics? See, thermo refers to as heat. So here basically we are going to study about heat and its conversions, right? So students, if I talk about the definition for thermodynamics, it would be branch of physical chemistry, branch of physical chemistry that deals with the study of heat and and its conversions is called thermodynamics. Now students, if I talk about the scope of thermodynamics, then thermodynamics basically explains us about the feasibility of a process, that basically a process has to occur or not, in which direction it will occur or not. Now what will be the extent of the process, to which extent it will occur or not, and the last thing is that efficiency of the process that it is occurring. Okay, so basically this is the scope of thermodynamics. If you need to write, you can also write this, that if I talk about scope of thermodynamics, then first of all, it explains us about basically about the process, the feasibility of a process. Next can be the efficiency of the process. Efficiency of the process, and the last is extent of the process, to which extent the process occurs, right? Now, if I talk about thermodynamics students in detail, then we move forward to our first term that we need to understand is, what do you mean by system? See, basically what we are going to do, we are going to understand some of the basic terms such as system, such as surrounding, such as universe. So first of all, as I've told you, thermodynamics is a study of heat and its conversions. Now the very basic terms that we need to here understand is all about system. See, the part of universe under my study, which I am investigating or which I am studying about, is known as system. See, if I read the definition of system, a specific portion of the universe. Now, the universe is comprised of two basic things, that is system as well as surrounding. It is a composition of system and surrounding, students. So, if I'm going to define system, I'm going to define in such a way that it is a specific portion of universe under study or under observation or under investigation, which is separated from the rest of the universe with a boundary. Okay, students. So if I talk about universe, it will be a sum of system as well as surrounding. Now, if I talk about system in detail, then students, system is the one which is under my observation or which is under my investigation area. The thing which I am studying comes under the category of what? Comes under the category of system, the thing which I am studying. For example, if I am studying about, the reaction that is occurring in a particular, I would say in a particular beaker. So my system will be the particular beaker in which the reaction is occurring. And the surrounding will be the rest of the area other than the system. So the universe will be the sum of system as well as the surroundings, right? Now, if I talk about system in detail, basically system can be further classified into three categories. One is open system, second one is closed system, and third one is isolated system, right? So now we are going to write the types of system over here. Types of system, it can be open system. It can be open system. The next one is closed system, students. And the third one which I'm talking about is isolated system. Is what? Isolated system. So whenever you're talking about a particular reaction, the reaction where it is occurring is basically the system of that area, right? Now the next term which comes about here is our surroundings. As I've told you, system is the one which we are studying and surrounding is other than system, right? So if I come to define surrounding, the rest of the universe which might be in a position to exchange energy and matter with the system is known as surrounding. In other words, I can also define surrounding in such a way that the area or the portion other than system in the universe is surrounding. Because universe is comprised of two basic things, system as well as surroundings. So if we subtract system from the universe, we are going to get our surroundings, right? So the definition can also be right in the same situation, in the same way as we are defining universe, right? So if I'm going to define surroundings, I would say that the area other than system is known as surrounding. And what happens there? It is already mentioned to you here that rest of the universe which might be in a position to exchange energy and matter with the system. Now both of the system and surrounding can exchange matter, can exchange energy. We are going to see in which of the cases the matter is being exchanged or in which of the cases energy is being exchanged. We are going to look forward towards that, right? Okay, now students, comes the type of system which I have already told you. System can be further classified into three categories: open system, closed system and isolated system, right? If I define system into three categories, one is open system, the second one is closed, and third one is isolated. Now what we are going to observe over here, we are going to observe about mass and energy. We are going to check all of these two things in three of these cases, right? If I talk about the very first system that comes in our mind is open system. Open system refers to when there is a complete transfer of mass and energy from system to the surroundings. It is known as open system. So if, let us say, I have this beaker with me, and it is open from the top. When it is open from the top and I am heating this, what I am doing, I am basically heating this over here. Now when I am heating, students, what is happening over here, I am heating this. So when I am heating this, if I have a solution over here, what do I observe? I observe that this basically convert into vapors. Now the conversion of vapors is basically what? The transfer of mass. Mass is being transformed. And if I talk about energy, then the temperature is being changed. So that will be the exchange of energy, right? So when we see the exchange of mass energy altogether, that is referred to as an open system. So open system is a system in which mass energy both can be transformed into system and surrounding. Clear, students? So we can write it that exchange of both mass and energy from system to surrounding. From system to surrounding, students. Okay, now if I talk about the very examples of this, one can be a cup of tea, another can be AC, students. Is it easy? Right. Now students, if I talk about the next kind of system that comes in our mind is closed system. Now what happens in a closed system? It is very simple, students. See, what we have done in the open one, and we'll compare it with the closed one, we see that now if I have this beaker, what I'm going to do, I'm going to put a cover over here. I'm going to put a cover over here. When I'm going to put a cover over here, now kindly tell me what will happen in the closed system. See, observation is a must process. If you see in the open system, it was open, right, from the top. So the mass and energy could be easily transformed. When I'm talking about closed system, only energy transform occurs between system and surrounding. For example, if I talk about pressure cooker in the cold conditions, so this would lie under the category of closed system. Other than this, students, I talk about all closed diathermic containers. Now, what are diathermic containers? In which heat transfers occur, right? So if I talk about the closed system, I would say only energy transform occur. Energy can transfer. Now here mass will not transfer. Do remember in your mind. And I've also given you examples. For example, pressure cooker in the cold conditions. Other than this, I've already told you all the closed diathermic container. Is it clear to you? Now the closed system is very easy. If you compare all the systems, it will be easy for you to understand. Now comes the next kind of system, which is known as isolated system. Now students, let us see all of these three cases and then we are going to define the isolated one. So if I'm going to see the open one, there will be complete transfer of the heat and the, of the mass and the energy. If I'm going to talk about the closed one, we are going to observe only the transfer of energy. Now when I'm going to talk about the isolated one, I'm going to see neither there is a exchange of mass nor there is an exchange of energy. So both of these won't exchange over here, right? So we are going to write over here, it is neither energy change occurs nor mass change or matter change. This system is called isolated system. This is called isolated system. Now it is very easy. For example, if I would say thermoflask, student, answer of this is thermoflask, an isolated system. Thermoflask. Wasn't it easy? It's so easy, right? Now students, moving to the next part, that is types of boundaries. First of all, we need to understand what do you mean by a boundary? A boundary, basically, if we talk in our general life, in a daily day-to-day life, what do we observe? What do you refer to as boundary? Boundary basically can be a line, can be a plane through which we are unable to pass through. For example, if I say there is a boundary over here and you can't cross this area and move to the another area, so that is referred to as a boundary, a line that I've been set for you so that you cannot cross and move to the another portion of the place where you are studying. Now what happens over here? See, the part which we are studying is referred to as system, right? And the part other than system is surrounding. Now if I talk about boundary, what can be a boundary? A boundary can be a line on an area which separates our system and surrounding from the universe. Clear? So if I talk about boundary, it is a line or an area which separates what? System and surrounding from the universe. Now what happens, students? See, if I talk about boundaries also, students, they are further classified. They are basically classified in three categories. If I talk about the very first category, that is real or imaginary. You can observe real boundary also, you can observe imaginary boundary also. For example, when you are moving through a car, okay, and there is some area which is prohibited, you can't move there. So there is a boundary set over there that you cannot move from your region to the region which is prohibited, which is no for you to move on, right? Now that area, that is a boundary which you can easily see, that is the real boundary. If I talk about the imaginary boundary which we create in our mind, or I would say which we can just imagine in the system which we are studying. So when I am talking about chemistry portion, we have classified boundaries into three categories. The number first can be real or imaginary. The number first is basically what? It is real or imaginary. Now the next one is rigid or flexible. It is rigid or flexible. See, there is nothing to learn in all of these, terms. You just have to understand with the respect of your day-to-day life. That's it. Okay, now the next kind of boundary that comes over here is diathermic or adiabatic. Diathermic or adiabatic. Now students, let us see one by one these kinds of boundary. If I talk about the very first kind of boundary, that is real or imaginary boundary. When I'm talking about real or imaginary boundary, let us say, let us take one example. If I say you, this is my beaker. Okay, this is the closed beaker. And if I'm talking about this beaker, this is open from the above, right? This is basically an open system. Why I'm writing open system? Because this is the portion which we are studying about, on which we are investigating. So this is referred to as a system. This is our open system and this is the closed one, which is closed from the top. So this is what? This is my closed system. Now what happens over here, the real boundary is the one which is visible to us. For example, in the case of closed container or closed beaker, we can easily see this line that it is closed from the top. That means this boundary basically is what? It is basically a real boundary. It is basically a real boundary. But when I'm talking about open system, students, I am unable to see any of the boundary. But yes, here lies an imaginary boundary. Which imaginary boundary? For example, there may be some liquid present over here in this beaker or in this system. So here the uppermost layer, basically this layer is what? This layer is an imaginary boundary. This is what? This is basically an imaginary boundary which is set up, which separates the liquid from the atmosphere, which is separating both of these. Now this is basically an imaginary boundary, while this is basically a real boundary. Here also liquid is present. Here also liquid is present. So if you talk in detail about real boundary, you will say the characteristics of what? You will say the characteristics of closed system. But when you are students talking about an imaginary boundary, then you are going to talk about the characteristics of open system. So both of these are quite simple. You just have to understand with the help of diagram, I would say that. Now if I move towards the next category of boundary, that is rigid or flexible. Now if I'm talking about rigid boundary is the one which is solid, which cannot be changed. And flexible is the one which we can move up and down with the help of a piston. How come? Let us see with an example, with the help of a diagram. Now here if I talk about, this is my open system again. If this is my open system, it is open from the top, I know that. And if it is an open system, here mass and energy both can be transformed from one region to another region. This is but obvious. But here students, what we need to understand over here is, for example, this is the liquid which is present inside here. Now if I put a piston over here in this beaker, if I'm going to put a piston over here, what is the role of piston? Piston either compresses it or it expands. What happens? We can move the piston like this. When we can move the piston below, then what will happen? It will compress. But when I'm going to take the piston back, it is going to expand. The volume is going to increase. So here what is happening? Here there is a flexibility. Volume can either increase or it can either decrease. How come it can increase or decrease? See, if I'm compressing through with the help of a piston, I'm pushing the piston downwards direction. What is happening? My volume is going to be reduced, right? When I'm moving the piston upwards, now how can I move the piston downward or upwards? It is with the help of a pressure. We are going to understand these all details in the coming segments. But first of all, we need to understand over here is what is a flexible kind of boundary. So flexible kind of boundary is the one in which we can either increase or decrease the volume with the help of expansion, expansion and compression. Compression will be the one in which we are putting the weight downwards like this. And expansion will be the one when the internal pressure will be more and it will be expanded. This boundary will move toward upwards. So this is basically what it is, a flexible boundary which lies under the category of open system, which is seen in the open system. So here you can also write this is flexible. Right? Now if I talk about the next category is the rigid one. That will occur in which case? Closed. In closed system. Closed system is the one which is closed from the top. Now here what happens? This is rigid in nature. Why this is rigid in nature? Because it is already closed from the top. So that's why we cannot put a piston and do these things. So basically in rigid boundary is observed in what? Closed system. Clear, students? Moreover, you can also compare in open system what kind of boundaries you can see. In open system, the very first you saw was imaginary boundary. Other than this, you can see flexible boundary. When I'm talking about the closed one, you have seen the rigid boundary. Also, you have seen in the previous case that real boundary is also observed in which case? In closed system. So you can, do in open and closed in such a way. Now talking about the next one comes the diathermic one. Now, diathermic or adiabatic, if I'm talking about diathermic, if I'm talking about the diathermic here, transfer of heat is seen. Transfer of heat occurs. When I'm talking about adiabatic, no transfer of heat occurs. No transfer of heat occurs. Is it clear to you? Now you can differentiate the kind of boundaries. You can differentiate the type of systems. Is it easy? Let us revise, students. What are the three kinds of system? Open system, closed system, isolated system. What are the types of boundaries? It can be your real or imaginary, rigid or flexible, diathermic or adiabatic. Is it clear to you? Now moving forward towards our next segment, that is, students, extensive properties. What do you mean by extensive properties? See what happens. Physical properties of the particles can be divided into extensive and the intensive one. Now if I talk about the extensive properties, these properties are the one which depend upon the mass of substance. Now this is going to be really very important. You have to mark this line as the most important line, with the help of which when you are given some of the questions, you need to identify between the extensive and the intensive one. The one thing that is going to help you to find extensive and intensive is that if it is dependent upon the mass of substance, it is referred to as an extensive one. But if it is not, dependent upon the mass of substance, it is the intensive one. Now let us take few examples of the extensive property. One of the example, if I talk about, is area, volume. These properties basically depend upon the mass of the substance. Other than this, I can talk about heat capacity. Don't worry, heat capacity we are going to study in the upcoming segments. And one more thing, in the extensive you could see heat capacity, but in the next intensive one you could see specific heat capacity. So students get confused in the question when they have given you heat capacity and specific heat capacity. You have to differentiate which one is extensive and which one is intensive. So do remember, heat capacity lies under the category of extensive property, while specific heat capacity lies under the category of intensive property. Other than this, students, what lies under the category of extensive one? It can be your energy. Energy also lies under the category of what? Extensive property. More than this, students, you can more write mass also. Now comes our next kind of property. Hopefully extensive is clear to you. The properties which depend upon the mass of substance. Examples are area, volume, heat capacity, energy and mass. Now moving forward to the next one, these are the intensive properties. As I've already told you while differentiating the extensive and the intensive one, that extensive are the one which depends upon the mass, while intensive will be the one which are here, which are independent of the mass of substance, which do not depend upon the mass of substance. Clear, students? Now what are the properties which do not depend upon the mass of substance? I want you all to just understand and just think for yourself. See, first of all, sit down and think what can be the property which do not depend upon the mass. See, I'm going to teach you each and everything, but I want you all to, apply your mind over the question upon the concept segments that yes, ma'am, this can be the property, this can be the property. So if I talk about pressure, just listen to me very carefully. If I talk about pressure, does it depends upon the mass of substance? No. Pressure doesn't depend upon the mass of substance. So that means pressure will come under the category of what? Intensive property. So here, if I'm going to write the examples for the intensive ones, the very first example, if I talk about, is pressure, students. Other than this, okay, just tell me temperature. What about temperature? Does temperature depend upon the mass of substance? No. Temperature doesn't depend upon the mass of substance. That means it will come under the category of what? Intensive property. So here the next example can be temperature. And yes, I hope so. You have already guessed this one. I have told you in the extensive one, heat capacity will come in the extensive one, and in the intensive one, what will come? Specific heat capacity. So, what will come over here? Specific heat capacity will come over here. Specific heat capacity will arise, right? Other than this, viscosity, students. Viscosity, molality. Okay, I'm going to tell you how. There are some of the cases which we are able to, just identify by looking at the question, but there are some of the cases that follow certain rules. Now, that rules to identify which is extensive, which is intensive, I'm going to tell you just after this. First of all, write all the examples. So, here, molality, normality. Okay. Moreover, pH also. See, pH also doesn't depend upon the mass of substance. It is independent, right? pH. Okay. Other than this, what can be various example? If I talk about density. Density. You will say, ma'am, how density? Wait. I'm going to tell you the rules, how to identify the extensive and the intensive one. So don't get discouraged over there. I will tell you how I have, put molality, normality, density over the intensive one. I'm going to tell you the rule. Don't worry. Other than this, students, mole fraction will come. Other than this, mole fraction will come. I want you all to also guess more over this. Like, if I talk about, we have done boiling point and melting point. What about them? Boiling point and melting point. Now, these are the examples of, students, what? These are the examples of our intensive property. Is it clear to you? Is it clear to you? Okay. Now, moving towards the rules to identify extensive and the intensive one. Basically, there are two rules that you need to understand over here. When you are going to divide two extensive properties, you are going to get one intensive property. So, the very first rule that we need to keep in our mind is what? Extensive property divided by extensive property leads to the formation of what? An intensive one. Now let us take one example of density. Let us take an example of density. Students, if I talk about density, what I need to understand over here is density. Basically, what is the formula for density? It is mass by volume. It is basically what? It is basically mass by volume. And I know that mass basically is an extensive property. Also, volume is basically an extensive property. We have written in the extensive one. See, some of the cases I've told you of the extensive, kindly remember the extensive ones. If you remember the extensive ones, intensive ones are, easy to find out, If you remember one of the properties, another one is easy to find out just with the help of these two rules, or either you can just keep in your mind that these are the extensive one, the rest over are the intensive ones, right? So here, if I'm talking about the mass and the volume, the mass is basically an extensive, and if I talk about the volume, it is also an extensive property. So when I'm going to divide two of the extensive properties, I'm going to get an intensive one. I'm going to get an intensive one. Right? Now, what is the next rule? This was our first rule. If I talk about the second rule, extensive properties, basically, students, are additive in nature. But if I talk about the intensive ones, these are non-additive in nature. So let us write this thing also. Extensive property are additive in nature. These are basically additive in nature, but intensive property are not additive in nature. These are not additive in nature. Is it clear to you? Now, if I move to the towards these cases which I've already mentioned over here, see, let us see the molarity case. What do you mean by molarity? Molarity is number of moles by volume, right? So number of moles are extensive by volume are also extensive. Extensive by extensive lead to the formation of intensive. Similarly, you can go for molarity, normality, density. We have already seen mole fraction. When mole number of moles are divided by total number of moles. For example, for a given component, you have to find the number of moles. For a given component, you need to find mole fraction. So what you will do, number of moles of that component divided by total number of moles. So now both of these are extensive property, so the resultant here comes out to be an intensive property. So now you can easily differentiate between both of these. And moreover, we are going to discuss about heat capacity, specific heat capacity. So for this time, I want you all to just remember this. When you're going to get the formulas for both of these cases, you will be able to differentiate which is extensive one, which is intensive one. Is it clear to you? Okay, students. Now looking forward towards the next segment, which is state function and the path function. See, first of all, if I talk about the state variables or if I talk about the state functions, I would say state variables or state parameters are the one which defines the physical state of any substance. When we define the physical state of any of the substance, that is referred to as a state variable or a state parameter. Now, if I'm going to differentiate between state function and the path function, I would say state function is basically the one which depends upon the initial and the final point. To remember this, state function, it is basically the one which depends upon initial point and the final point. Now, if I talk about the next one, which is the path function is basically the one which depends upon the path, or I would say, the region through which the process is occurring. That is the path, right? So, path function is the one which is dependent upon the path. Okay, now that would be referred to as what? Path function. State function is the one which is dependent upon only the initial point and the final point. Is it clear to you? Now, if I talk about both of these, if I'm going to differentiate the state function and the path function, let us say, take a few examples over here to understand which of the following are the state functions and which of the following are the path functions. Now, students, if I take case of heat work, let us say if I'm talking about the very first case, that is heat. The next one is work. The next I can take an example is pressure, volume, temperature. Now let us find out which one is state function and which one is path function. See, if I am talking about heat and if I am talking about work, both of these lie under the category of path function because they depend upon the path in which the reaction is occurring. But if I am going to talk about the state function, that is, I am talking about the initial and the final position, then I am going to see that pressure, basically, if I talk about delta P, what do you mean by delta P? Change in pressure. Now, how do you calculate change in pressure? That means final pressure minus initial pressure. So what are you talking about? You're talking about the 2 points. You're talking about the initial point and the final point. So whenever, students, you are considering initial and the final position or the initial and the final point, it is referred to as what? It is referred to your state function. But if you are talking about the path in which the reaction is occurring, that is the path function. So here, as I told you, for example, you can, you have already done in your numerical portions about delta P. There is a change in pressure. So whenever we are talking about change in pressure, we are talking about 2 points, initial and the final one. So basically this lies under the category of what? State function. Now if I talk about the volume, you can correlate with this again with the pressure one. If I talk about volume, I always say that basically delta V. What do you mean by delta V? It is V2 minus V1. That means final volume minus initial volume. That means here also you are talking about 2 points, initial point and the final point. So here also I can say that volume is a kind of state function. If I talk about temperature again, now whenever I'm talking about delta T can be small delta T dt or a capital delta T. Now small dt refers to the small change that is occurring in a substance in the states, and the big delta T refers to as the big change that is occurring in the following states, right? Now, basically, it is also a kind of state variable because here also we are talking about the final and the initial point. So this also lies under the category of state variables. Now, as I have told that heat and work, they both basically depend upon the path in which the reaction is occurring. So both of these students basically are path function. Both of these lie under the category of path function. Hence, you are able to differentiate between the state and the path function. One more, internal energy, if I take example, internal energy that is represented by delta U or delta E basically also is a state function. So they can ask you the same question. Now moving forward towards the next segment, students, that comes out to be a thermodynamic process. In the thermodynamic process, let us take the very first process is our isothermal process. See, if I talk about isothermal process, if students you have seen the lecture of states of matter, then you are able to define isothermal very easily. But if you have not seen, no need to worry. I'm going to tell you again. What do you mean by isothermal process? Iso refers to as same. Whenever you're talking about isothermal, isobaric, isochoric, in all of these, iso refers to as same. Now what you need to do in chemistry, whenever you are studying a term, you need to differentiate, or you need to divide the term into two categories or three categories. You no need to just keep on remembering each and every term. You just need to divide it into two parts. This can be iso and another one is thermal. Iso refers to same, thermal here refers to temperature. When you are going to observe that there is same temperature, that means temperature here is kept as a constant. Now, what are the state variables if I talk about? There are basically certain parameters. The very first parameter if I talk about is our pressure, volume, temperature. These are the three parameters, right? Now, if I've kept temperature as a constant, now what relationship I will establish? I will establish the relationship between the leftover. Now, what are the leftover? Pressure and the volume are the leftover. So, a relationship which is established between pressure and volume is basically a Boyle's law. Now, what does Boyle's law state? Boyle's law state that pressure is inversely proportional to volume, students. Now, if pressure, we talk, is inversely proportional to volume, what is the following graph we are going to obtain between pressure and volume? We are going to get this curve. Now, this is the curve for what? This is the curve for isothermal case. Right, we are going to get this. And moreover, in the isothermal, one formula which we derive from pressure that is inversely proportional to volume from the Boyle's law is P1 V1 is equals to P2 V2. So is it clear to you? Hopefully this graph is clear to you for the isothermal one. Now comes our next thermodynamic process, students, which is isobaric process. If I talk about again isobaric, I'm going to divide this term into two parts. One is the iso, another one is the baric. Now what do you mean by bar? Bar basically is the unit of pressure. That means here what is kept as a constant? Here pressure is kept as a constant. So we are going to write constant pressure or same pressure. Again, students, now see, when students pressure is kept constant, we are going to observe a graph between again pressure and volume. We are obtaining all of the graphs with respect to pressure on the y-axis and volume on the x-axis. So see, here is the pressure, here is the volume. When pressure is kept constant, that means a value will be same for pressure and the volume can change, right? For isobaric, it is a constant pressure. So if I say this graph is going to come like this. Clear? This is going to be our graph. Now if I talk about the next process, that is isochoric. For the case of isochoric, we observe that in isochoric there is going to be same volume. Clear? Now for same volume, what is the graph we are going to obtain? See, here is the pressure, here's the volume. Volume is now kept as a constant, but pressure can change. If pressure can change, we are going to get this graph. Okay, we are going to get this graph. Now moving forward towards the next thermodynamic process, which is the adiabatic one. Now we are going to put all of these processes in a single diagram, so no need to worry about it. Adiabatic process is the one in which no heat exchange occurs. That means delta Q will be 0. Over here, what we are going to observe, that delta Q, that means heat exchange is going to be 0. There will be no heat exchange. Now if I talk about the cyclic one, cyclic one is the one which starts from an initial point and which comes back to that point again. that is the cyclic one. It creates a cycle. Now here for the cyclic one also, if I'm going to draw a graph between pressure and volume, I'm going to get this graph. If I'm starting from this point, I'm moving in this direction, and this creates a cyclic. This is a cyclic process. Clear? Now let us make all of these graph together. If I'm going to draw all of these graph together, what I'm going to obtain over here, let us see. For the very first case, what we did for the very first case was isothermal. First of all, I'm going to make individually, then I'm going to combine all of these. See, individually, if I talk about isothermal, I got to see this graph, right? If I'm going to talk about isobaric, that means the pressure one. That means the pressure one when the pressure is kept as a constant. This was the isobaric one. If I'm talking about the isochoric one, when the volume was kept as constant, this was the graph for the isochoric. Now, if I'm going to combine all of these graphs together, see, this question is asked in your examination. On y-axis, you are going to see pressure. On x-axis, you are going to see the volume. Now, what you're going to observe over here, they are going to give you some of the lines, and they want you to understand and to find out which of the following thermodynamic process represents the particular line. So, first line is this. Second line is this, then you're going to get this, and at last you're going to get this. Now you have to identify over here, students, which is A, which is B, which is C, and which is D. You have to identify these four processes, thermodynamic processes. If I talk about the very first one, A1, what do you observe over here? The pressure is kept as a constant, but the volume keeps on increasing. Pressure is kept as constant. Whenever the pressure is kept constant, it is referred to as isobaric. Now this line represents isobaric. Here, if I talk about the B one, basically this is for our isothermal, when temperature was kept constant. Now if I talk about the C one, this is for adiabatic, students. This one is for adiabatic. And at the last, if I talk about the D1, it is basically the constant volume. When there is a constant volume, it is isochoric. Now this one refers for the isochoric process. Is it clear to you? You can easily check all of these. You can easily check over here. This one was your isochoric, this one was your isobaric, and this one was your isothermal. Is it clear to you? Great. Now this is really very important. You have to put a star mark over here on this one. Clear? Now we will move towards 1 second. Okay. Now we are moving towards our next segment, that is going to be reversible process and the irreversible process. This I guess you have already done in your lower standards, in your lower classes in 10th standard, or I would say. So here, what do you mean by reversible and irreversible? You would say, ma'am, reversible is the one in which the reactant can be converted into product, and product again can be converted into the reactant one. And if we talk about irreversible one, they can't be converted, but it is quite a different process. I am here talking about thermodynamics. When I'm talking about thermodynamics, I am referring to reversible and irreversible with respect to the steps in which the reactions is occurring, or with respect to the time in which the reaction is occurring. See, if I talk about the reversible process, I would say it takes infinite time to complete. Now, reversible process basically is a slow process. Okay, the very first difference I would write, it is a slow process. If I talk about the irreversible one, it is a fast process. The next point of difference which I can write in the reversible one is that it takes infinite time to complete. It takes infinite time to complete. While if I talk about, students, the irreversible one, it takes a finite time. That means a particular time to complete the reaction. So it takes finite time to complete the reaction. Clear? Other than this, if I talk about these, I have already told you it is a slow process, it is a fast process. It occurs in small step, while it occurs, only in one step. So the next point of difference can be, it occurs in small steps. Small steps. But if I talk about the irreversible one, it occurs only in a single step. Single or one step, you can write. Other than this, students, what happens over here when it is occurring in small steps? No, each and every step is in equilibrium with the previous one. Remember this. Here, equilibrium arises with each and every step. One step with the previous step, it is in equilibrium. One step with the previous step, it is in equilibrium. But if I'm talking about the irreversible one, what happens over here? There is no equilibrium found in between the steps. It generally is occur in single step. So the equilibrium that is attained is over initial or at the final position, not in between. So what do we write at the 4 point over here is that each step is in equilibrium with the previous one. With the previous one. Now, if I talk about the irreversible process, here no equilibrium occurs. No equilibrium occurs in between the steps. Either you can observe equilibrium at the initial point or at the final point. So this ends our segment of reversible process and the irreversible process. Now students, moving towards our next segment over here, we have understood what do you mean by the reversible and what do you mean by the irreversible. Now you can easily differentiate between both of these, right? If I'm going to define heat, what do you mean by heat now? The next segment comes out to be heat. Heat basically, students, is a form of energy. First of all, if I'm going to define heat, I guess you can also define the same in a very, easy language. What is heat? Heat is a form of energy, right? Heat is a form of energy. Other than this, students, if I ask you about, heat being a state function or a path function, we have already seen that heat is a path function. It is basically a path function which depends upon what? Which depends upon the path. It does not depends upon the initial and the final point. Clear? Other than this, what is the unit of heat? It is joule, right? The unit of heat is joule. Now the most important thing that we need to understand over here in chemistry, which is different from the physics concept, is that heat given to the system and heat given by the system. So if we talk about chemistry, heat given to the system, the very first, and the next one is heat given by the system. Okay, now if I'm going to tell both of these, when the heat is given to the system, that means someone is gaining something. So when someone is gaining something, it becomes positive, right? So here heat given to the system comes positive, and heat given by the system. For example, I am the system and I am giving the heat. I'm losing something, that means I become a negative. So here heat given to the system will come positive, while heat given by the system will come negative. Do not get confused between physics and chemistry. I'm again and again telling you, here heat given to the system comes out to be positive and heat given by the system comes out to be negative. So whenever you are given the question in your numerical section, you need to see the question very carefully. They will mention you over there that heat given to the system is 19 joules. So you need to see that if heat is given to the system, you are going to take the value as a positive value. But if there in the question it is written that heat given by the system is 19 joules, you are going to take heat in the form of negative. That will be minus 19. Is it clear to you? So this was all about heat, students. It was very simple. Now comes the next part, which is heat capacity, which is quite important for you to understand in the thermodynamics chapter. Heat capacity is basically the amount of heat required to raise the temperature of the system by 1 degree Celsius. Now we need to, we need some amount of heat that will increase the temperature by 1 degree Celsius. Amount of heat required to raise the temperature by 1 degree Celsius. Is it clear to you? We, represent it by capital C. We represent heat capacity by capital C. And what is the formula for this? The formula for heat capacity is Q by delta T. This is the formula for heat capacity. Now further, heat capacity is classified into two categories. One is a specific heat capacity, another one is molar heat capacity. If I'm talking about specific heat or molar heat, I will define it in the terms of heat capacity only. But how I'm going to define it, listen very carefully. If I talk about specific heat capacity, I will say that amount of heat required to raise the temperature of 1 gram of a substance. But when I'm talking about a molar one, I will say 1 mole of a substance. This is the basic difference that you need to remember over here, that amount of heat required to raise the temperature by 1 degree Celsius of 1 gram of substance. Of 1 gram of substance. That will be your specific heat capacity. Now at constant volume and at constant temperature, what is going to be the formula, students? If I talk about at constant volume, CV is basically Q by, now remember this, here we are talking about 1 gram. So we are going to take mass over here and delta T will come. And if I'm talking about at pressure, it is going to be Q by again M delta T. This is going to be a formula for the volume, for the, pressure. Now comes the next heat capacity, which is molar heat capacity. Students, molar heat capacity is quite similar to specific heat capacity in the terms of raising the temperature. But we need to raise the temperature for 1 gram of substance in the specific heat capacity. But in the molar heat capacity, we will raise the heat by 1 degree Celsius of what? Of 1 mole of a substance. So I would define it as amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. Now see, there we used small cp, small cv. Here we are going to use capital CP, capital CV. So if I talk about capital CV, that is again going to be Q by now N delta T will come. Here number of moles will come, their number of, their mass was there. Grams was there, right? Here Cp will be equal to Q by N delta T. Now if I talk about the relationship between Cp, capital CP, capital CV and the small cp, small cv, it comes out to be capital Cp basically is what? It is the multiplication of M into small cp. That means this capital Cp is molar heat capacity at constant pressure, and this small cp is what? It is a specific heat capacity at constant pressure. Now if I talk about again at volume, capital Cv is molar heat capacity at constant volume. It will be equivalent to M into small cv. That means into specific heat capacity at constant volume. Okay, and the relationship between small cp minus cv is equals to R. This is the relationship with respect to R. Okay, so you can correlate all of these formulas. These all formulas are quite important. Now students, moving to the next segment that comes out to be work. Work is quite simple. If I need to push a table, okay, from one place to the another place, so what I would do, I will put a force on that table, and the distance that it displaces with respect to the force applied in the direction of the displacement, it is referred to as work. It is quite simple. You have done this in your 10th standard also, that force applied and the object displaces it in that direction in which force is applied, it is referred to as work done, right? So work done is basically the force applied into the displacement. Now this basically is change in displacement. How much is the object move from your initial position to the final position in which the direction of force is applied, right? So here dl basically refers to the change in displacement. You can also make the diagram as I've told you. I am displacing a, object from one place to another. You can also make the diagram. So this is the general formula which we used to study in the 10th standards. Now, if I talk about, in more detail about the work, here we need to find out pressure volume work. For that, we need to understand what do you mean by expansion, what do you mean by compression. So first of all, we are going to make two diagrams over here to understand expansion and compression in detail. See, work expansion and work compression. What are both of these situations? See, we have what? If I put a piston over here and if I put a piston over here. Now, in the very first case, there is a gas which is present over here. There is a gas over here. And moreover, there is a gas over here also. So here, what will happen? In both of these beakers, the gas will exert some pressure in the upward direction on the piston. So here I would say this is the pressure exerted by the gas on the piston. This is the pressure exerted by gas on the piston, which I am writing by P gas. Here also the same situation. This is the pressure exerted by gas on the piston. So it is also again P gas. Now what happens? If I say there is also one external pressure that we are applying from the piston, we are moving the piston in the downward direction and the gas is applying the pressure in the upward direction. So what is happening? Two kinds of pressure are being exerted, one by the gas, another by the piston. So if I say this is the pressure exerted externally, this is pressure external. Here also I can say, now I am taking two cases over here. If I say, kindly listen very carefully. If I say pressure of gas is more than pressure external, what will happen? If it is more, it will move in the upward direction. If it is moving in the upward direction, what is going to happen? The volume is going to increase. When the volume is going to increase, it is the case of what? Expansion. So this is the case of what? Expansion. This is work expansion. If I say pressure of a gas, students, is less than the pressure external, that means this pressure external is more. If it is more than the internal one, it will move in the downward direction. When it will move in the downward direction, what will happen? The volume will decrease. The volume will decrease, hence it is the case of what? Work compression. Is it clear? So this is compression. So I have basically explained you two kinds of things. One is expansion and another one is compression. Now moving forward to the expression for the pressure volume work. If I talk about compression expansion, the basic formula that you need to keep in your mind is for your work done. See, work done is basically minus P external delta V. Kindly keep this formula in your mind. Okay, now what we need to do over here is we need to find for both of the cases, for the expansion, for the compression. If I talk about work expansion, what will be work done? Is it positive or negative? See, for the case of work expansion, if I move to the previous diagram here, this was the expansion case, this was the expansion case. What was happening in expansion? When pressure of the gas was more, it will move in the upward direction and the volume will increase. When the volume will increase, that means volume is going to be positive. Delta V is again going to be positive over here, and we know that here, according to the formula I've told you just right now, that W basically is equals to minus P external delta V. So here if I say delta V is positive, then the whole term here basically is multiplied with negative. That means work done comes out to be negative. Work done comes out to be negative. For which case? For the expansion case. If I talk about the compression case, if I talk about the compression case, what do I observe over here? Delta V is going to be negative. Why it is going to be negative? Now let us move towards the previous diagram. Here the pressure external was more in comparison to the pressure of gas. So if pressure external was more, it is moving in the downward direction. This area, this volume is basically going to reduce. Now volume when going to be reduced will comes out to be negative. When it is coming out to be negative, students, what I will say? W is minus P external into delta V. Now delta V is negative. It is also multiplied with the negative term. Negative into negative comes out to be what? A positive value. So work done comes out to be positive value for the case of what? Compression. So it is quite simple for work expansion and compression. For work expansion, W is coming out to be negative. For work compression, it comes out to be a positive value. Okay, students. Now moving towards our next segment, we have seen the work expansion. We have seen the work compression. Now we are going to see the work done in the isochoric process, in isobaric process, in isothermal process, in all of these processes. Now for the very first case, I'm going to see the isochoric process. Work done in isochoric process. Now what happens in the case of isochoric? You all know now, iso refers to same. For choric we say same volume. Now when there is same volume, in other terms I can say that volume is constant. When volume is constant, that means delta V comes out to be 0. Is it clear to you? I hope so this is clear to you. When delta V comes out to be 0, you know that W is equals to minus P external delta V. Now delta V comes out to be 0, so W also comes out to be 0. That means work done in the isochoric process comes out to be a 0 value. Now if I talk about the work done in the case of isobaric process, I would say work done in the case of isobaric process. Now for the case of isobaric process, students, what happened? Isobaric refers to same pressure, right? So here same pressure is seen. When same pressure is seen, that means constant pressure is observed. When constant pressure is seen, then we know that the formula is W is equals to minus P external delta V, and it is going to be constant. The formula is going to remain as it is. So the work done for the isobaric process is same which we have derived for the, which we know the formula for the work done. But in the case of isochoric, it tends to be 0, right? Now we will see the next case over here, students. If I talk about the next case, that comes out to be reversible isothermal process. Work done in reversible isothermal process. See, first of all, let us revise what do you mean by isothermal. Isothermal was the one in which temperature was constant. When temperature was constant, we found a relationship between pressure and volume, that pressure was inversely proportional to volume. With the help of Boyle's law, we also derived a formula which was P1 V1 is equals to P2 V2, right? Now if I'm talking about work done in the reversible isothermal process, the formula that comes out to be here is W is equals to minus nRT log to the base 10 V2 by V1. Basically, this is your formula. Here, one second, here log E will come, then we will convert it into log to the base 10. So when we will convert it into log to the base 10, then what will come? It will be minus 2.303 nRT log to the base 10 V2 by V1. Now as I've told you, this is basically isothermal process. So here we know that for isothermal, P1 V1 is equals to P2 V2. So what I can say, I have to replace this V2 by V1 with the terms of the pressure. See, either you can get the question in terms of volume or you can get the question in terms of pressure. So we need to find both of these formulas. So here what I'm going to do is, I'm going to take P1 by P2. I'm going to take this P2 downward over here and V1 downward over the V2. So this is what I'm getting. Now I'm going to replace this over here. When I'm going to replace this over here, what is the formula which I'm going to derive? I'm going to get is work done is equals to minus 2.303 nRT log to the base 10 P1 by P2. Now this formula is quite different from the formula which we have studied. Students get confused and they just remember that V2 by V1 will come, and so they replaces the pressure also in the similar way. They write P2 by P1, but exactly it is not the correct one. Here P1 by P2 will come. Why? Because we know that according to the isothermal process, Boyle's law is being followed, which is equivalent to P1 V1 is equals to P2 V2. So when we are going to replace V2 by V1, it comes out to be P1 by P2, not P2 by P1. So this is the basic thing that you need to keep in your mind. While solving the questions, also re-revise your formula. Either make a formula sheet or paste it on your cupboard. That would be a best way, so that you can re-revise daily, or at a place where you go day in and day out. So that will be easy for you to revise formulas, and when you revise formulas and put the concept in your question segment, then you are able to solve the questions, right? So this is the basic thing that students do wrong. They just write V2 by V1 as P2 by P1, but it is actually P1 by P2, right? Now students, one more formula we can replace. What formula we have written in the previous one? We wrote minus 2.303 nRT log to the base 10 P1 by P2. But for example, we don't have number of moles, we don't have temperature. Then what we will do? How we will calculate work done? We know that, students, for the ideal gas, PV is equals to nRT. Now for whatever the situation it is given to you, if you have been given with the first state, for example, you have been given P1 V1, then you can use this formula and replace nRT by P1 V1. If you have been given with P2 V2, kindly replace it with P2 V2. So for example, if I am writing P1 V1 is equals to nRT, so I'm going to replace over here. What I'm going to get? W is equals to minus 2.303 into P1 V1, or either you can write P2 V2 with respect to your question, okay, into log to the base 10 P1 by P2. So this is one more formula that you can derive for the case of isothermal, reversible isothermal process. Now if I talk about the irreversible isothermal process, I am talking about irreversible isothermal process. Now what happens in irreversible isothermal process? Here basically if I take the case for vacuum, when I'm talking about vacuum, in vacuum, P external, pressure external tends to be 0, hence work done tends to be 0. So if I'm talking about in this case, when P external is 0, that means in vacuum work done comes out to be 0. But for the case of adiabatic, but if I'm talking about which case, I'm talking about the adiabatic one in which there is no transfer of heat. So Q tends to be 0. When students Q tends to be 0, what is the basic formula that we here need to remember is W is equals to NR. Now here gamma minus 1 will come. What do you mean by gamma over here? Gamma is the ratio of Cp by Cv. We have already done Cp/Cv. So it is the ratio of Cp by Cv that we need to calculate. And now with respect of temperature, we are going to write it T2 minus T1. This is the formula for work done for the adiabatic. There is no need to derive it because it is the one-shot video lecture and then you have to practice for your examination. So once you have seen this formula, now kindly equate it in the question segment. It will be easy for you. Clear? Okay, students. Now moving towards our next segment, that is the first law of thermodynamics. It is quite simple. I know you all know, but still we need to remember this. We need to revise it, right? Now, what do you mean by first law of thermodynamics? It is basically the conservation of energy. That energy can neither be created nor be destroyed in any chemical reaction, right? So you can either write it is conservation of energy. It is what? It is conservation of energy. Energy can neither be created nor be destroyed in chemical reaction. In any chemical reaction. Okay, now what is the basically, the mathematical expression for the first law of thermodynamics? It is delta U is equals to delta Q plus W. Now, what do you mean by delta U? It is the internal energy. Q, is heat and W is the work done, right? We can replace the work done by minus P delta V, P external delta V. So, the new formula which we get over here is this. Clear, students? So this is basically your first law of thermodynamics. Now students, let us see the next term, which is internal energy. If I talk about internal energy, basically every substance is associated with definite amount of energy that is called internal energy. All the energies are comprised together and form the internal energy. So basically if I talk more about internal energy, it is represented by U. Change in internal energy. Change in internal energy is represented by delta U. After this, students, if I ask you, is it a state function or a path function? I've already told you it is a state function. Okay, now let me ask you one more thing. It is an extensive property or an intensive property? This is an extensive property. This is an extensive property. Hopefully internal energy is also clear to you, students. Now moving towards the next segment, that is enthalpy of heat content. If I talk about enthalpy of heat content, basically is what? It is heat absorbed at constant pressure. Either I can write in such a way or you can directly write heat content of a system at the constant pressure is called, it is called enthalpy. Kindly correct it. It is enthalpy. It is enthalpy. Now students, if I talk more about enthalpy, basically it is represented by H. It is represented by H. And we do not calculate the value of H, we calculate the value of change in enthalpy. We always calculate the value of change in enthalpy. And change in enthalpy, students, is represented by delta H. It is represented by delta H. Now, what is the formula for the enthalpy? It is basically delta H is equivalent to delta U plus P dV. This is the formula for the change in enthalpy. Now students, we already know that. What we know that this is work done. We know that other than this, we can write the first law of thermodynamics, which is equivalent to delta U is equals to delta Q. We have seen this case, delta Q plus delta W. Okay, now what I'm going to do over here is delta U is equals to delta Q minus P dV. If I'm going to take this term over here, what I'm going to get? This is the first law, right? What I'm going to get? Delta U plus P dV is equals to delta Q. Now, can I replace this over here? When I'm going to replace this over here, what I'm going to get over here is delta U basically, sorry, delta H is equivalent to delta Q at constant pressure. So this is the definition for the enthalpy, that the heat, extent of heat change at the constant pressure. Is it clear to you? Heat content of a system at constant pressure is enthalpy of the system. Now students, moving to the next part of the enthalpy topic is the relationship between delta H and delta Q. If I talk about the relationship between delta H and delta Q, first relationship that we have just seen right now, delta H is equals to delta U plus P delta V. We know this thing very carefully. We have seen this. We also know this, that PV is equals to nRT. We know this thing, PV is equals to nRT, so we can replace it for the chemical reaction. For a chemical reaction, this formula which I'm going to derive over here is quite important. Here you can calculate delta H is equals to delta U. Now this delta sign will come over here, delta nRT, and we know that R and T are constant, so they will come outside. Delta H is equals to delta U plus RT delta Ng. Now why G I have written over here? G refers to the gaseous form. And how to calculate delta Ng? That is number of moles of product minus number of moles of reactant. This is very, very important. And this formula which we have derived over here is quite important also. You are going to see a lot of questions with the help of this formula. Clear? This is for a particular kind of reaction, students. Now students, moving to the next part, that is going to be exothermic reaction and the endothermic reaction. We are going to study about endothermic reaction and another one is exothermic reaction. Now see, if I talk about endothermic and the exothermic, in the endothermic reaction, energy is basically absorbed. And in the case of exothermic, it is released. So here energy is absorbed. Here energy is released. Here energy is released. Now, other than students, what happens over here? See, energy is absorbed. That means what happens? The reactant require energy and then they will convert into the product. So if I'm going to draw a graph, energy profile diagram over here, what I'm going to see, the reactants acquire some amount of energy to get converted into product, because here energy is absorbed. Here it require energy. This is our reactant, this is our product. It is the energy profile diagram. These are the phases over here. Right? If I talk about the exothermic one, what I'm going to see over here, energy is released. That means reactants are being converted into product and energy is released. What I'm going to show over here is reactant will have more energy than the product because energy is released. Here we need amount of energy, so the reactant has a less amount of energy as compared to product. Here reactant will have more amount of energy. Here again energy will come, here phase will come. Is it clear to you? This was the difference between endothermic reaction and the exothermic one. Now students, come our thermochemistry. These are quite simple. I'm going to tell you one by one. First of all, what do you mean by standard enthalpy? Here again and again you are going to see the standard term. Standard basically is delta H naught. Not. Now, what do you mean by standard? Standard is basically when temperature and pressure are fixed. When pressure is, 1 atm and temperature is 298 Kelvin, then we would define standard enthalpy as it is the enthalpy change accompanying reaction when all the reactants and products are taken in their standard state. So, when I am talking about all the reactants and the products in the standard state, standard enthalpy for them is going to be 0. For example, if I am talking about delta H naught for Cl2, it is 0. delta H naught for Br2, it is 0. Means that when they are occurring naturally or in free state, they are 0. Naturally or in free state, it comes out to be 0. More than this, students, you can also take for hydrogen also, for H2 also. Okay, if I talk about delta H naught for H2, it is also 0. That means these elements, when they are in their free state or in their natural state, the standard enthalpy tends to be 0. Now, students, comes the enthalpy of combustion. If I talk about enthalpy of combustion, it is defined as heat change when 1 mole of a substance is completely burnt or oxidized in the presence of oxygen. For example, if I am taking CH4, in the presence of oxygen, it converts into CO2 and water. So what is the enthalpy of basically combustion? Over here you need to find out that here always 1 mole will be present. When you have been given here, for example, 6CH4 plus 6O2, you have to convert, you have to divide all of them, and you need at least 1 mole. Then only this definition will be accurate. And here the heat change which is occurring, the heat change which comes out to be here, is known as enthalpy of combustion. So what would be definition? It is defined as the heat change when 1 mole of a substance is completely burnt or oxidized in the presence of oxygen. Is it clear? Okay, students. Now comes our next, enthalpy of heat of formation. Now what do you mean by formation? Formation refers to as to combine something, right? So see, heat change when 1 mole of substance from its elements is formed under given temperature and pressure. Now here we need to see the formation. In combustion, what we did? In combustion, in the presence of oxygen, we did the heating. Now in the case of formation, we are forming something under temperature and pressure. So here if I see, this is the general example. If this is the general example, that AA plus BB plus C gives CC plus DD. Here small a, small b, small c, small d are basically coefficients. For example, if I say there is a reaction 2A plus 3B gives 4C. So here 2, 3, 4. These are basically the small letters which I have written over here. These are the coefficients. Now to calculate the enthalpy for the heat formation, which is represented by delta H formation, what you need to do is heat of, the extent of heat of product minus heat of reactant. And how you have to do this? For the product, what you have? C. You have this coefficient, you need to multiply this C. You need to multiply this C with the heat content, right? For the heat content of the heat of formation of, C, okay, plus D into heat of formation for D. Now you have to subtract it with the reactant one. Now here for the reactant, A into heat of, formation of A plus B into heat of formation of B. This is the general formula that you can apply over here for solving this question segment. Now comes enthalpy of phase change. If I talk about phase change, what do you mean by phase change? For example, carbon in the diamond form is being converted into carbon into graphite form. That means it is the phase transformation, right? Now, the heat change takes place when 1 mole of one form changes into another. So the heat change that is occurring is referred to as heat of phase change. Now comes enthalpy of hydrogenation. What do you mean by hydrogenation? It is addition of H2, right? So see here, amount of enthalpy change that takes place when 1 mole of unsaturated compound is completely hydrogenated. Let us see one case. If I talk about CH2, double bond CH2, now it is being hydrogenated. What will happen in the case of hydrogenation? One H2 will attack on this carbon, another on this carbon, breaking this double bond. And while breaking this double bond, it will convert into what? An alkane molecule, which is an ethane, right? So here you have seen what? Amount of enthalpy change to convert this into this, to convert the unsaturated compound into the saturated one. This is basically what? This is enthalpy of hydrogenation. Is it clear? Okay. Now students, moving towards the Hess law. What do you mean by Hess law? Now we are going to see. This is quite important with respect to your question segment. Now students, if I come to define Hess law, it is going to be really very important for your examination. What does Hess law states us that? It states us that whenever a reaction is occurring, it can either occur in the steps or it can either completely occur in a single step. But for both of these steps, the total amount of heat evolved or absorbed is almost the same, either whether it is occurring in a number of steps or it is occurring in a single step. So what it is going to be defined as the total amount of heat absorbed or released in a chemical reaction which is either occurring in a single step, or in multiple steps, you can write in your bracket also more than one step, is same. Now this is what is Hess law. So the total amount of heat evolved or absorbed in a reaction is same whether the reaction takes place in a step or a number of steps. Now let us take one case for the Hess law, students. If I take one case for the Hess law, for example, I'm taking the case for the formation of carbon monoxide. Let us see the formation of, this is the question, okay, which I'm writing. Calculate the heat, involved in the formation of carbon monoxide. If I'm going to write this, for the formation of carbon monoxide, you have been given two reactions, students. The very first reaction that is given to you, reaction 1 is given to you. Carbon plus O2 gives CO2. And here the heat is X1. Delta H is X1. Okay, now the reaction number 2. If I am talking about the reaction number 2, this was the reaction number 1. For the reaction 2, you have carbon monoxide plus half O2 gives again CO2. You have, students, this reaction, and for this reaction delta H tends to be X2. Kindly calculate for the formation of carbon monoxide what will be delta H. So it is very simple. First of all, for the one you need to calculate, kindly write the reaction. I want to form CO, carbon monoxide, and I know that to form carbon monoxide I require carbon and oxygen. To form what? Carbon monoxide. Now to balance it out, I know that in the reactant side there is one carbon and in the product side is also one carbon. But if I talk about oxygen, in the reactant side it is O2, but in the product side it is only single oxygen. So can I divide it by half, because I have to form a single product. So yes, I have to find delta H for this reaction, and I have these reactions. So according to Hess law, whenever a reaction is taking place either in a single step or in a multiple step, their delta H is going to become equal. Their delta H will be equal. So for this, if we are going to calculate delta H, that will be equivalent for this case, right? So in this case, see what I'm going to do. If I subtract reaction 2 from reaction 1, what I'm going to get over here, if I'm going to subtract, see, carbon plus O2 minus CO minus half O2, and in the product side what I'm going to get, CO2 minus CO2. Now both of these CO2 are divided over here. Okay, no problem, students. Now see what happens here. Carbon plus O2 minus half O2 is half O2. And this carbon monoxide is in subtraction form. It will move to the product side, will form what? Carbon monoxide. This is what we acquire. This is what we acquire in the reactant side. So what I'm going to do, I am going to subtract this from this. That means the delta H for this reaction, what it is, it will be X1 minus X2. So in your question paper, you are going to find out a lot of questions just like this, where you have been given the value for the X. Just you have to put the value of the X and you need to find the answer. Is that clear to you? Great. Now students, comes our applications of Hess law. It is quite simple. One of the application already I have told you. See, if I see the application of Hess law, first application is calculation of enthalpy of formation. If I talk about calculation of enthalpy of formation, again we have already done the enthalpy of formation when something is being formed, right? So the heat released when we get 1 mole of a substance, right? Hess law is useful to calculate the enthalpy changes for the reaction which are experimentally not possible, for whom we cannot calculate. Hess law is going to help us, right? For example, there are large number of compounds such as C6H6, C2H6, etc., whose direct synthesis from their constituent elements is not possible. Clear? Okay, the enthalpy of formation of such compounds can be calculated with the help of Hess law. Like, you will be given a certain reaction and you will be given the reaction is occurring in in certain steps. So for the certain steps you can calculate delta H, that will be equivalent for the main reaction. Is it clear? Just we have done the same case. Now the next comes the determination of the standard enthalpies of the reaction. Hess law used to help us in this also. With the help of standard enthalpy of formation of reactant and product, the standard enthalpy of reaction can also be calculated. Hence, delta H naught is the sum of standard heat of formation of product minus sum of standard heat of formation of reactant. See, we have already done in the previous case, that was HP minus HR. That means the heat content for the product minus of the reactant. It is the similar case. You know, it will be a similar case. Now comes, students, our next segment that comes out to be entropy. If I'm going to define entropy, what do you mean by entropy? Entropy refers to as the randomness of a molecule. If I'm going to define it, it is basically the randomness of a molecule. Now students, if I talk about solid, liquid and gas, just see, I am talking about solid, I am talking about liquid, I am talking about gas. Which will have more randomness? See, if I'm going to draw solid, liquid and gas over here, my solid is the one in which particles are tightly packed, like this, and liquid will be the one in which particles are not tightly packed. They are at a distance from each other, but yes, not at a far distance. But if I talk about the gaseous one, what I'm going to observe over here, the particles are present at a very far distance. So what do you mean by here entropy? Entropy refers to randomness, the ability of a molecule to move in different directions. This is basically what is entropy. If I talk about this very first molecule over here, if I talk about this one, is it able to move in here in this portion? No, because it is tightly packed, because they have the strong force of attraction, so they cannot move over here. But if I talk about liquid, yes, this particle can move over here, over here, over here in this direction. But if I talk about the gaseous one, it has a lot of space to move. Why they have a lot of space? Because they have more repulsion as compared to attraction forces, right? So if I talk about the randomness, the gases will have more randomness than liquid, than the solid one. Solid will have the least randomness. Now comes the formula section, students. If I talk about the formula sections over here, what is the formula for entropy? That is delta S. Delta S is basically change in entropy. Just similar to the previous case, as I've told you, in the enthalpy one, we represented by H. Now here we are represented by entropy. When we are representing by entropy, we are going to divide heat with respect to temperature. Is it clear? This was the formula of entropy. Now students, moving forward towards the depth of entropy, first of all, we will calculate for the isothermal process. We will calculate for which process? For isothermal process. Okay, now when I'm talking about isothermal process, I know that in the case of isothermal process, temperature is going to be constant. When temperature comes to be constant, delta U is also 0 for this case. Delta U is also 0, internal energy is also 0. When internal energy is also 0, and I'm talking about delta S, I know delta S is Q by T. And for isothermal, T is constant. Now when T is constant, and you need to calculate over here about Q. If I ask you, calculate Q reversible. How can you calculate Q reversible? Let us calculate Q reversible, because temperature over here is constant. To calculate Q reversible, basically there is a simple formula that you need to remember over here is negative of minus 2.303. Okay, negative of minus 2.303 nRT log to the base 10. This we have done, V2 by V1. This was the formula. This was the simplest formula. Now students, what we are going to do over here, it is quite simple. To obtain delta S, we are going to divide it by T. When we are going to divide it by T, then this T will be cancelled. So delta S comes out to be 2.303 nR log to the base 10 V2 by V1. This is the formula that we are going to obtain for delta S. Now for the case 2, if I talk about the adiabatic one. For the adiabatic one, delta Q is 0. Now students, if delta Q is 0, it is but obvious delta S will be 0. Why? Because delta S will be 0 because it is Q by T. If Q is 0, then delta S is 0. Now if I talk about the next case, that is the isochoric one. In the isochoric one, what do you see? Volume is going to remain constant. Now students, for the previous case, if I talk about isochoric one, here we are seeing the volume is constant. If volume is constant, what is the formula for delta S? If I talk about delta S students, then here we need to put the formula of QP. We have done the formula for Q with respect to CV and CP. The same we are going to equate over here. Now what is the formula? It is NCV. First of all, NCV, then ln T T1 by T2. This is going to be the formula. Sorry, we are taking V2 by V1, so here T2 by T1 will come. Here T2 by T1 will come. Okay, this is for the case of isochoric when volume is kept as a constant. But you remember, when we are going to take our isobaric process, then for isobaric process it is the same. It is the same. Just here Cp will come. It is going to remain same. So this was all about our processes. Other than this, students, you can do for fusion also, for vaporization also. For fusion, you need to divide it basically by the freezing point. For vaporization, you need to divide it by the boiling point. This was all about this segment. Now moving forward towards our next segment, that comes out to be second law of thermodynamics. Now what do you mean by second law of thermodynamics, students? Now students, coming to the definition of second law of thermodynamics, first of all, this states us that entropy of universe always increases in every spontaneous change. Okay, so now what do you mean by spontaneous change? First of all, we need to understand this thing, students. If I talk about, there are two kinds of changes. One is the spontaneous one, another one is the non-spontaneous one, right? So if I'm talking about spontaneous process, another one is non-spontaneous process. So basically, spontaneous is the one which occurs on its own, right? And non-spontaneous is the one which doesn't occurs on its own. We need something, to at least initiate the reaction, to initiate and to complete the reaction. This can be once initiated. This can be once initiated to proceed, but for this we need to complete the overall reaction. This can be initiated or which can occur on their own, but it needs someone to complete the complete reaction, right? So we can write it occurs on its own or either be just initiated. But if I talk about the non-spontaneous one, okay, doesn't occur on its own. Is it clear? Now students, other than this, here there is no need to supply energy. Here we need to supply energy so that the reaction could complete. So we can write here, no need to supply energy. And here all I can say is that we need to supply energy so that the reaction could complete. We need to supply energy over here. Okay, students. Now, this was the very basic difference. If I would say for the spontaneous reaction, spontaneous process, if I say, running a river, I would say, or river floating down a hill, this is the kind of spontaneous process because it is flowing likewise. Or a melting of ice is an example of spontaneous one. But if I talk about the non-spontaneous one, I would say the separation of ink in water that can be separated on its own. You need to separate it out through the distillation process or the different processes. That means you need to do some work over here. So that comes into the category of non-spontaneous, which cannot be occur on its own. Now students, if I talk about the second law of thermodynamics, as I've already told you, it is basically what? It is basically very simple law. It defines us that entropy of a universe, entropy we have just studied, that is delta S for the universe, always increases in every spontaneous change. Now let us see how it always increasing. Let us see this also. If I take two systems, students, that means, for example, if I'm taking this as my system which I am studying, it is basically supplying or losing heat, I would say, to the surrounding. it is actually losing q amount of heat to the surrounding. Now what is happening over here, if I'm going to find out the delta S for both of these, if delta S for the system, what will be equivalent to, basically we know that delta S is equals to q by temperature. Here it is supplying, that means it is losing something, that means here heat comes out to be negative, that means minus q. And let us say it has a temperature of T1, it has a temperature of T2, so here T1 will come. Now this is for the system. Similarly, we can do for the surrounding. We can calculate delta S for the surrounding. If I calculate delta S for the surrounding students, again I know delta S basically is Q by T. Here it is gaining heat. When someone is gaining heat, it is acquiring with charge, positive charge. That means here positive Q will come, and at what temperature? T2 temperature. But students, we know that universe basically is a sum of system and surrounding, right? So we can write universe is a sum of system plus surrounding. Is it clear? Now we know that delta S for universe will be equivalent to what? Delta S for system plus delta S for surrounding. Right? Now see what happens over here. Now see what is going to happen. For the system, first of all, we are going to calculate for the universe. For the universe, we need to add both of these. And for the system, we have seen minus q by T1. And for the surrounding, it is minus q by T2. Is it clear? Is it clear to you? Now, what we are going to do over here, just it is right the same thing. Now, what we need to do over here is we will common out q. When we are taking q as common, what we are going to get? Minus 1 by T1 plus 1 by T2. Clear? Now, if I take the LCM as T1 and T2, or you can directly see over here what is happening. Q bracket starts, if I take LCM T1, T2, what I'm getting over here is, it has T1, so it will be minus T2 and it will be plus T1. In other terms, what I can write over here is Q into T1 minus T2 divided by T1, T2, which is equivalent to delta S universe. So can you please tell me that delta S universe is more than 0 or less than 0? It is more than 0. That means it always keeps on increasing. So this defines our which law? Second law. This defines our second law, that delta S for the universe keeps on increasing. It is more than 0. So the second law here states that this law states that entropy of universe always keeps on increasing in every spontaneous change. Hence we have also proven this in our case, in this case. Is it clear to you? So now students, moving to the next topic of ours, that is the free energy. Okay, if I talk about the free energy topic, let us see what do you mean by free energy. First of all, delta G, we always calculate change in free energy. We never calculate directly free energy, just like the enthalpy, just like the entropy, right? If I talk about delta G, basically it is useful, non-expensive mechanical work. Now, what do you mean by non-expansive and expansive? Basically, expansive refers to what? In which there is a change in volume. But when there is no change in volume, we are not able to calculate work done with respect to pressure, with respect to volume. Then in which terms can we calculate work done? We calculate work done in the respect of free energy. How come? See, G is equals to H minus T delta S. Basically, this is the formula. Now, we know that what happens over here, what happens at constant pressure and temperature, at constant pressure and temperature, what we are seeing, delta G, we always calculate change in free energy, right? Change in Gibbs free energy, it is equivalent to delta H minus T delta S. Now, this is the formula that you are going to apply on many of the questions. Clear, students? Now, whenever you are going to get delta G as a negative value, that comes out to be a spontaneous process. Sorry. It will be your spontaneous process. But when your delta G, students, comes out to be a positive value, it comes out to be a non-spontaneous process. This is also going to help you a lot, because it is also asked, in the spontaneous process the delta G tends to be negative, while in the non-spontaneous it tends to be positive value. Is it clear? It was quite easy, right, students? Now, students, this ends our chapter over here. Now we are going to start with the question segments. Now, if I talk about the question segments, let us read the very first question over here, which is, assume each reaction is carried out in an open container. Okay, for which reaction will delta H equivalent to delta E? Now let us see. We know that according to the formula, which was our formula? Our formula was delta H is equals to delta U plus P delta V, and we have replaced P delta V with nRT. Do you remember the equation? Delta H is equals to delta U plus RT delta NG. Now, if we are able to calculate delta NG, I guess the relationship between them will be easy, because we need to find out delta H equivalent to delta E. Right? Now, for delta H equivalent to delta U and delta E is the same thing. Internal energy can be represented by U, can be represented by E. It is the same thing. It is the same thing. So, we need to be equivalent to this. If we want delta H to be equivalent to delta U or delta E, which is the same thing, we need this to be 0. Now, how it will come to be 0 when delta Ng is 0? Now, what do you mean by delta Ng? Change in number of moles for the gaseous one. Now, only for the gaseous one, number of moles of product minus number of moles of reactant. Now, let us see in the first case. Here, 2 is the number of moles of product. And for the reactant, it is 1 plus 1. When nothing is given to you, it is 1 plus 1. So, here delta Ng is equivalent to 2 minus 2, it tends to be 0. So we need this delta Ng to be 0, so that delta H is equals to delta U. That means A option is our correct answer. Still, you can calculate for the other cases also. If I see the B case, see, it is 2 plus 1 when nothing is given, 3. 3 minus 2. We don't consider solid, we are taking for the gaseous state. So 3 minus 2 is 1. Here delta Ng comes out to be 1. So we can say delta H is not equivalent to delta U in this case. Now if I talk about this one also, 1 plus 1, 2. 2 minus 1 is again 1. So delta Ng is not 0 over here also. If I see this case over here, 2 minus 2 plus 1, 3. So minus 1. So delta Ng is again not equivalent to 0. So for the case of first, it is equivalent to 0. Hence the answer comes out to be option number A. Okay students, now moving forward towards the next question. The enthalpy and the entropy change for the reaction Br2 plus Cl2 gives 2 BrCl are 30 kilojoule per mole and 105 kilojoule per mole. Okay. Here, kindly see, sorry, I spoke kilojoule. It is here kilojoule per mole, but here it is joule Kelvin per mole. Here it is given to you kilojoule, so you need to convert it into joule, so you need to multiply it with 10 raised to the power 3. Okay, students, skip this step. So do remember this. After this, the temperature at which the reaction will be in equilibrium is. Now you need to calculate the temperature when there is an equilibrium. Now what are the options? A option is 285.7 Kelvin, B option is 273 Kelvin, C option is 450 Kelvin, and D is 300 Kelvin. So here if I talk about this question, it is quite simple. Here we are being given with enthalpy and entropy. If I talk about enthalpy, that is delta H, it is 30 into 10 raised to the power 3, because we have converted into joules, right? Now if I talk about entropy, which is delta S, it is given to us 105. Right students, other than this students, what they have given us, they have given us that we need to find temperature at an equilibrium. So when I'm talking about equilibrium, delta G is 0, and the formula delta G is equals to delta H minus T delta S. This is the formula which we have just studied right now. When it is 0, then delta H minus T delta S, let us take this minus T delta S over here, which comes positive. T delta S is equals to delta H, temperature we need to find. So delta H divided by delta S will be the temperature at the equilibrium. Now delta, basically see, T is equals to delta H upon delta S. Now what is delta H? It is 30 into 10 raised to the power 3, and what is delta S? It is 105. Is it clear to you? Now when we are going to divide it, the option comes out to be option number A, which is 285.7 Kelvin. Is it clear to you? Okay, now students, moving forward towards the next question. The work done by 100 calorie of heat in isothermal expansion of ideal gas is. Now they have given us condition of isothermal expansion over here, right? And one more thing students, see, I have taken many cases: isobaric, isochoric, isothermal, adiabatic. So you need to practice it. And how you will practice it? Listen to the video first of all, then revise by yourself, then make a formula sheet, and then apply on the questions. This would be a better way to do questions, right? Now if I talk about here, we need to find the work done. Okay, work done by 100 calorie of heat. That means heat has been given to us 100 calorie, and we know that for heat the unit is joules. So we need to convert this calorie into joules, and 1 calorie, students, is basically equivalent to 4.18 joules. Okay, now if I have to convert this 100 calorie into joules, it comes out to be 418 joules. Now this is the heat. This is the heat. We have been given the heat, and moreover, we need to find the work done. So it is quite simple. We know this formula. Delta U is equals to delta Q plus delta W. We need to find out delta W. We know that for the isothermal expansion over here, delta U is 0. So it comes out to be delta Q plus delta W. So delta Q is minus delta Q is equals to delta W. Right, students? Now what does delta W comes over here? We know that it is 100 calorie of heat in this isothermal expansion of ideal gases, students. Is it clear to you? So here, what answer will come? It will come 418 joule. The work done comes out to be 418 joules, right? So our answer will be option number A. See, negative and positive sign basically represents your expansion contraction, right? So whenever you are, the heat is given to the system, heat is given by the system. So it represents the process that is being occurring. Okay, so the answer here comes out to be option number A. Now moving to the last question of our video lecture. Temperature and heat are not. A option is extensive property, B option is intensive property, C option is intensive and extensive property respectively, D is extensive and intensive properties respectively. So students, we have already done that extensive properties are the one which depend upon the amount of substance. That means upon the mass of substance, while intensive are the one which do not depend upon the mass of substance. So if I am considering the case of temperature over here, if I talk about temperature, it does not depend upon the mass of substance. So if temperature is not depending on the mass of substance, it will be which property? Intensive property. Now if I talk about heat basically depends upon the mass of substance, so which it comes under which property? Extensive property. So which option will be correct? No, both are not extensive, because this is our intensive, this is extensive. Both are not intensive, so C option will be correct. The very first one is extensive while the another one is intense. Very first one is intensive while the another one is extensive property, right? Now students, I guess we are done with the questions. No, one more question is there with you. The work done by a system is 8 joules when 40 joule heat is supplied to it. The change in internal energy of the system during the process will be: A option is 32 joules, B option is 40 joules, C option is 48 joules, while D option is minus 32 joules. So students, it is very quite simple formula. Delta U is equals to delta Q plus delta W. Now, you need to see work done by the system is this much when 40 joule heat is supplied to it. You know, when you are supplying something, it turns out to be positive, but when someone is doing something, it is negative. Work is done by the system, so work done is here negative. So it will be minus 8 plus. Here heat is supplied to the system, we are getting something. If I am getting something, I will be positive. But if I am doing something, I will be negative. I am doing 8 joule of work done. That means it is minus 8. And I am getting heat of 40. That means it is a positive value. So you just need to, see the signs. So it is 40 minus 8, which comes out to be 32. Which comes out to be 32 joules. That means option number A will be our correct. Is it clear to you? I hope so. You have easily understood the chapter very well. I just want you all to make a formula sheet for the chapter thermodynamics, because in the physical chemistry, the more and more formula sheets you are preparing, you will be easy to do this in your examination time. When there is examination approaching towards you, you don't have to do the equations, you don't have to derive them. You just have to read the formulas, then you have to put the formulas in the question segment and re-revise it. So first of all, listen to my video, then read your notes. After reading your notes, I want you all to write the formulas which we have derived without looking at the notebook which you have made, the notes which you have made. And if you are not getting the formulas, if you're forgetting it, kindly review the video again, see the video again, read the notes again, do this process 1 time, 2 time, thrice time. It will be easy for you, right? So students, to end this chapter, I would say that practice daily, because the quality of your practice determines the caliber of your performance. So we end this chapter over here, and we will meet in the next chapter. So till then, keep smiling, keep learning, and do practice DPP, because I have taken all the previous year questions in the DPP section. So do practice and keep practicing. Thank you so much. Have a good day.